Welcome, MAP4C, day 61. The lesson is 6.7 applications of exponential equations, the last day of new stuff on chapter 6. And it's a bit of a long lesson, so you're going to have to strap yourself in here. Thankfully, it's nothing really new. It's review of stuff we've taken this chapter and last chapter. We're kind of combining them into one lesson. So even though there's several examples, I'm hoping that it's nothing too difficult. The 3-minute review is kind of a reminder of last chapter, distinguish between exponential growth and decay in real life situations. So they just want us to put a circle exponential growth and put a box around exponential decay. Well, exponential growth is stuff that's going up, and the graph's easy to see. That one's exponential growth. That one's exponential decay. It's going down, right? On the equation, what shows exponential growth? It's when the base is more than 1, right? That's going up. The base is more than 1. So this is growth. And since this one isn't more than 1, it's less than 1, it's going down, whatever the application happens to be, and we saw some of these last minute. On the table, well, we know it's exponential growth and decay, so we can see this one's going down. So this one's decay, but how can we tell from a table if it's exponential decay, or maybe this is just a linear table? Remember, what we do is it's the common ratios. So we would take the second thing and divide by the one that came before it. That's a divide sign, and that's 0.5. And in fact, that's how these are all getting cut in half, right? The base for this one would be a half. And similarly here, if I went 55 divided by 50, that's 1.1. Actually, you can check that on your calculator. Each time I'm going up by 1.1. So here, this table, the base would be 1.1. And in fact, we practiced a little bit last chapter. This model would be the initial amount, and the base is 1.1 to the exponent x. Well, we're going to be solving equations like this graphically. This one is growth. This one is decay. All right, let's get at it. Applications of exponential equations: solve real-life problems using exponential equations. Dandy. Okay, there's an exponential model. We saw this last chapter, and we did regression and all that business. It represents exponential growth if b is greater than 1, right? If the base is greater than 1, then it's growing. And we actually thought of this as 1 plus r, where r was the growth rate, right? R was the percent rate that it was growing. Similarly, the same function would represent exponential decay if b was less than 1, right? Like 0.96 was the equation on the 3-minute review. And we thought of this one as 1 minus r, where it's a little bit less than 100%. So in the example here, and that's a beaut. That's a beaut truck, that is. The good old Uncle Ferd's fraud pickup. It's a beaut. It's given by this equation, and we can see that it's a decay question, right? Because the base is less than 1. It's a decay question. Where T is the year since 1992, and that was a fine year for trucks, 1992. And the value is in thousands of dollars. So this 14, this output, whatever I put in for T, is going to give me a value in thousands of dollars. So the first question is to explain the parts of the model. So 14, remember that A value, that's the initial amount, right? The initial amount, and in this case, the initial value was 14. Well, not 14, 14,000 bucks. So Uncle Ferd paid 14,000 bucks for that butte in 1992. The 0.78, that's the base, right? And it represents exponential decay. Well, how much is it? Well, it's less than 1, right? 1 is the cutoff if it stayed even. So how much is it decaying by? It's decaying by 0.22, 22% a year. That's the decay rate. And T, of course, is the time that's gone past since 1992. When will a truck be worth less than $1,000? Well, it's hard to believe that that truck will ever be worth less than $1,000. But how do we solve this if it just follows this model? Notice that this is the output, right? This is V equals 1,000. Now notice that V is the value in 1,000. So what's the value of V here actually? It's when V is 1, right? So we have to solve this equation. Well, we solved these equations yesterday when the unknown was in the exponent. We want to figure out how many years. That's T. T is what we want to find. And we actually saw 3 different ways yesterday. Okay? The first way was guess and check on our scientific calculator. The second way was using the TI-83 and a graph. The third way was TI-83 and a table. Now, in this type of question, since it doesn't say for you to use any particular method, you could choose any of these, okay? Any one of them. You're responsible for knowing all 3, but you're going to get to sort of do your own way. We've got 3 examples today, and I'm going to just sort of do each, one question each kind, just to, so if this is your favorite kind, you'll see a solution your way. If this is your favorite kind, you'll see a solution your way. But it's really up to you if it doesn't ask for a specific way. So in guess and check, what do we mean to do here? Well, essentially, we guess at a value of t and then calculate the right side. We want to calculate that expression on our scientific calculator and see if we can get this to be 1. Right? So how many years has to go by for the value to decay to $1,000, or a value of V equals 1? So you might, who knows? Make a guess. Try T equals 5. Then you pound that into a calculator. I'll just do this one calculation and then fill it in from now on. So I go 14 times 0.78 to the exponent 5, 4. So that's 4.04. Notice that means after 5 years, Uncle Ferd's fraud pickup was still worth $4,000. So that means we need it to decay more. This number needs to be higher. So if we try 10, and now I'm just, you would keep using your calculator, but I'm just reading this off of my notes now. That's 1.167. So still, this is worth $1,100, almost $1,200. So it still needs to decay more. So we might try 12 years. But after 12 years, the value is 0.71. Right, 0.71. It's decayed too much. I want this value to be 1. I want the output to be 1. So I got to go in between these 2 values. Let's try 11. Well, 11 gives me a value of 0.91. That means it's still decayed too much. It's got to be between 10 and 11. And I'm just going to keep guessing here. Try 10.5 or 10.6. You keep on guessing and checking values. You keep on putting this into your calculator, ... and eventually you end up with a value around 10.6 gives you 1.005. That's within $5. That's pretty good. So we would say, therefore, it would take 10.6 years to decay to a value of $1,000 about. Okay, and that was using the guess and check technique. That was using this one. And in the next couple examples, we'll see the other ones. Okay, let's keep going. Some other applications are very specific: doubling time and half-life. And doubling time is got to do with exponential growth. I see because the base is more than one. This is growing, and this is used for things like, populations growing and values of investments growing. And the whole idea, it's very similar to this, except for we've got a base as 2 because we're interested in how long it takes for something to double. As far as what these letters are represent, well, A is the amount at the end, and that would be the amount of the population or the amount of the investment or whatever. Little a is the initial amount, just like it was before. 2 is the base. D is what's called the doubling time, and that's where this formula gets its name. And this is kind of a strange thing. This is the amount of time it takes something to double. Okay? Amount of time it takes something to double. So for instance, if it was an investment, if you had $100 sitting in the bank and it's earning a certain amount of interest, how long it takes to reach $200, your investment, double from 100 to 200, is D, the doubling time. T, just like we would expect here, is the amount of time that's gone by. That's just the amount of time. All right, and this is a common application of exponential growth. Exponential decay has to do with half-life. Now, sometimes you see it like this, the formula, and sometimes you'll see it with its decimal half-life, like this. Maybe this one's easier to put into your calculator. I will leave that up to you, whether you like the fraction or the decimal. These are equivalent. Most of these things are the same. This is still the amount at the end. A is the amount at the start still. And H is what's called the half-life. Half-life is often used in radioactive substances that are decaying. Radioactive substance decay, and it's how long it takes for an object's size, whether it's mass or value or population, whatever, it takes for something to decay to half its amount. So, for instance, in Uncle Ferd's fraud pickup there, how long it started at $14,000. How long it took it to get to $7,000? That's the half-life of Uncle Ferd's truck. How many years it took for it to go from being worth $14,000 to $7,000? That's the half-life. T is the time again, and we'll see an example like this in example 3. Example 2, the population of Drefton is 4,000. How are we doing for time? I might cut this video in half. Yeah, let's do that. It's running long. I told you to strap yourself in. We got 2 videos today.